Thanks, Davide. Thanks for inviting me to give this lecture. It's really a pleasure, an honor for me to start this school. Let me mention that I can really confirm that it's a school where you make a lot of friends, because I was here back in 2009. It was really a blast. And just as a curiosity, it was back then that I first met Agnese Bissi, so it's nice that now, it's a nice coincidence that now we are both teaching. So yeah, the topic that, can I start? It's already, okay. The topic that I was assigned is methods and techniques in non-perturbative quantum field theory. Of course, as you can imagine, there are many things that one could use to fill this title. And what I picked is, I decided to discuss some examples of quantum field theories in low dimensions that we know how to solve using particular technique, which is the large N expansion. Okay, so what we're going to do is to go through these examples and see how to solve them. So the topic is going to be QFTs in 2D and 3D that are strongly coupled. And we can solve using large N. Let me start by giving some motivation and introduction to this topic. I should also say that please stop me at any point with questions. And also a logistic thing, I thought we could do like 50 minutes, then we do 5 minutes break, and then another 50. So now it's 11. Okay. So let me mention some motivations. So really the most important motivation, in my opinion, is that you should think about these models that we're going to discuss as toy models, meaning that if you're interested in the study of quantum field theory, you want to understand some difficult formal properties of quantum field theories that are beyond perturbation theory. So whatever idea you come up with, some conjecture, something you want to test, really the first thing you should do is to take these simple examples and try to work it out in them, okay? And this is something that I have kept doing in my research, and then that's why also I got affectionate to these models. And so test ideas about QFT at strong coupling. And more specifically, the models that we're going to discuss have a lot of features that are in common with the theories that are important for the description of nature, but that are strongly coupled. I'm talking, of course, about four-dimensional abelian gauge theories. So let me just throw some names of phenomena that are common between these simple examples that we are going to discuss and four-dimensional abelian gauge theories. So one thing is we are going to see example of symmetry breaking that happens at strong coupling. We are going to have theories with asymptotic freedom and dynamically generated scale. If you don't know some of these words, don't worry, because we are going to discuss them. Generated scale. This theory feature S matrices with interesting, these theories have a matrix with interesting features, such as bound states that emerge from coupling or resonances. Another thing that they have is that sometimes they display interacting RG fixed points, which is also something that we see in non-abelian gauge theories in 4 dimensions, in the so-called conformal windows. And also in these examples, we will have examples of this. And the existence of these interacting RG fixed points will require us to discuss a little bit of conformal field theory, and this has a lot of connections to things that you will see also in other courses in this school. So we are going to have some taste of QFT. And finally, maybe since it's just one more, we're also going to see examples of theories that have Regge trajectories. The spectrum of masses of massive particles organizes in Regge trajectories, similarly to what happens in non-abelian gauge theories like QCD. And finally, maybe let me add it here. They're also interesting because they have themselves applications to condensed matter and statistical physics. Of course, depending on your interest, you might weigh some of these motivations more than others. So let me now discuss the plan. So what is going to be the plan of the course? So after some introduction, we are going to start discussing. So let me give you now the list of examples that we want to study. We're going to start by studying what is called ON model in 3 dimensions and in 2 dimensions. After that, we're going to go to the so-called Gross-Neve model, also in 3D and 2D. Then I want to discuss the example of quantum chromodynamics in 2 dimensions with fundamental matter. This is also sometimes called Toft model. And if time permits, depends also on how we go along, but we will also try to touch on the topic of QCD in 2 dimensions with adjoint matter fields. And I should say that the main reference for these the first 3 bullets that I discuss here are all papers that came out in the same year, and this year is 1974. So it's not really the latest development in physics, but I still think it's good to learn about them. And I will give you now the reference in a second. While if you arrive here, this is related to more recent developments. That is still an active research topic. So what are the references? I will now give you the references to the papers, but I put also on the website some reviews that you can look at. So for the ON model, the paper that discusses it is by these authors. And the year is 1974, as I said. The second one, not surprisingly, it's the paper by Gross and Neve. This is the one about the 2D model. For the 3D one, it's a bit scattered, but there is a very nice review that collects a lot of results. And so for the 3D Gross Neve, the review, the reference is a review by Rosenstein. The reference that I suggest is a review by these three authors. For the third one, the paper is the paper by Tuft, as the name suggests. And finally, for the more recent developments, we are going to mostly discuss what is contained in a recent paper, 2021, by Dempsey, Klebanov, and Pufu, and some of their references. This is for QCD with adjoints. So you can give a look at these references beforehand if you want to follow better. Okay, so having said that, now we're going to start with the more technical part. Any questions? Okay. So I will not immediately go through to the first bullet of my plan, because before I want to give some introduction to these quantum field theories in dimension less than 4, and also to the technique of large N that we're going to use. So let's start with some introduction. So I want to just make a simple but I believe interesting remark about studying quantum field theory in dimension less than 4 and strong coupling. Okay. So the observation is that asymptotic freedom and strong coupling in the IR happens for the simplest Lagrangians. For the simplest Lagrangians, we can write in, when we go to dimensions less than 4. And let me remind or explain why. So the possible Lagrangians are built out of, so suppose we want to do really Lagrangian quantum field theory, so we want to start by picking some fields and writing down some possible interactions between them. And the important thing to keep in mind is the dimensions. So we can build the Lagrangians out of scalar fields, which by dimension analysis like they have this dimension in energy. Fermions, which have, so D is always going to be for me the space-time dimension. I should have mentioned this. So this parameter D is the space-time dimension. And A mu gauge fields, which have dimensions 1. So these are scalar, fermions, and gauge fields. So now, when we go and try to build Lagrangians out of them, there is an accident that When we do that in 4 dimensions, all the things that we write down, all the interactions that we write down are basically classically marginal. So if you start writing down, for instance, a quartic interaction between the scalars, there is just this cute coincidence. I don't know if anybody came up with an argument of why this happens exactly in the dimensional spacetime that we appear to live in, but okay, so there's just I don't think there is an argument, it's just a curiosity, that all of these operators are all of dimension 4. Okay, so if you just use that number that we put above, you can see that. The only exception is if we write down some cubic self-interaction for the scalar. But okay, this guy by itself is not very nice because it gives a potential unbounded from below, so it's not so common to study this field theory. And this means, and please ask if, or we can go more in details if you're not familiar with this argument, but this means that the associated coupling constants, the coupling constants associated to this coupling, they're all pure numbers, at least classically. They're all classically marginal. And at the quantum level, so couplings are classically marginal. At the quantum level, you might have computed at least some of these beta functions in your QFT classes. They all become marginally irrelevant, with the notable exception of marginally irrelevant, with the exception of the non-abelian gauge theories, with only exception of which is why people were so surprised when they computed for the non-abelian gauge theories. So the simple remark I wanted to make is that this story is completely different when we go to lower dimension. In lower dimension, each of these simple Lagrangians has a coupling constant which has a positive mass dimension. So all of these give relevant interactions. Okay, which means that our coupling has positive mass dimensions. So what does that mean? So if we draw a cartoon picture of the RG for these theories, this is the energy scale. So if you start with some free theory in the UV, and then we turn on some of these interactions, what happens is that the coupling constant, let's call it lambda, the coupling constant lambda sets a scale. Okay, so this is the scale set by our coupling constant. And then imagine that you want to compute some observable in this theory. Let's say an observable that is characterized by a typical energy scale E, and you try to use perturbation theory to compute your observable. Then what you're gonna find is that, okay, we can factor out some power of the energy scale, and the power is going to depend on the mass dimension of our observable. And then we're gonna go and try to compute this observable in perturbation theory. And you see, what can the perturbative expansion depend on? Well, it can only depend on the ratio between our coupling and the energy scale, right? The energy scale at which we are computing our observable. And so you see that having this kind of, so what conclusion can we draw immediately from here? The conclusion that we can draw immediately is that when we go at energies which are below the scale set by our coupling, this perturbative expansion breaks down. You see, because lambda over E becomes large. So here, the perturbative expansion breaks down. And as a result, all these simple Lagrangians that in 4 dimensions were, oops, did I knock my microphone? Yes, I did. All these simple Lagrangians that in 4 dimensions were had marginally relevant couplings, they all lead to a strongly coupled IR in lower dimension. Okay? So that was the first observation that I wanted to make. And so this suggests that if we really want to understand what happens here, if we want to understand what happens at low energies in these theories, we will have to rely on some different tools than the ordinary expansion in the coupling. Okay? Are there questions about this simple dimensional argument? Hmm? For which one, in what sense? For which theory, you mean? I meant, I'm just assuming here that the coupling constant sets some scale, okay? And I call this scale lambda. And you can check that in all these examples, for instance, in 3 dimensions, if you consider the gauge coupling of, or you consider the Yukawa interaction, or you consider the quartic interaction, all of them set some scale in our theory because they're dimensionful. Okay, so in all of these examples, you cannot possibly discuss what happens in the IR in these theories unless, like by using ordinary perturbation theory. Your ordinary perturbation theory is going to break down. Okay? So what do we do in this case? We need to invent, yes? Lambda is the coupling, so it depends a little bit, since in this argument I fixed lambda to be something which has dimension of 1 in energy, okay? So it depends a bit what's the dimension of your coupling. So it might be that it's some power of your coupling. For instance, if your coupling has dimension of energy squared, then this lambda will be the square root of the coupling, and then maybe you will, okay, in this argument I was assuming that the coupling has energy dimension 1, but you can adapt the argument to the other cases.
I don't understand very well the difference between lambda and the energy.
You don't understand the difference between lambda and the energy? So lambda is, so imagine this thing, this, what I mean by observable, which depends on, suppose you're scattering some particles, okay? And then E is going to be the center of mass energy, okay? And lambda just your coupling constant, whatever you have in your Lagrangian, okay? And I'm saying that suppose you want to go and compute it in an expansion in the coupling. So the expansion on dimensional grounds can only be in these ratios, okay? And I'm saying that once you have these ratios, you're doomed, because when you try to go to large distances, your expansion is going to break down. Okay. So that was as a motivation for trying to look for some other tool to study these theories. And one nice tool that people discovered is the Largen expansion. Okay, so let me give now some general introduction to Largen. So we have an additional expansion parameter. An additional expansion parameter, which is 1 over n, when n is, let's say, that controls the number of fields, So in this course, we will concentrate on examples in which our fields are vectors, meaning that they have one index, and this index runs from 1 to this number n, which is the one that we're going to use to do the expansion. And I'm using this ambiguous letter chi because I don't want to commit to whether my fields are scalars or fermions. For the moment, you can just be agnostic about it. This can be a scalar or a spinor. Okay? And so this is what we call vector. And don't get confused, it just means vector in the index that goes from 1 to n, not in the spacetime index. And as a result, this type of models, they're called vector models. Okay? When we do the Largen limit with these fields with one index. And then there are also a very important and well-studied class of examples in which our fields have two indices, and these are called matrix models. And I will maybe just make some parenthetical comments on them, but the main object of our interest will be these vector models. So we are going to study these theories, and we assume that there is a symmetry that allows us to rotate these indices. Okay, and this symmetry might be either UN or ON, depending on whether chi is complex or real. Okay, depending on the reality condition that we put on our fields, we might have slightly different symmetries. I think I can go. And this symmetry can be a global symmetry of our theory, or it could be something that we gauge, meaning that we only consider physical operators to be the ones that are invariant under this symmetry. That's not really important, okay? That's for the purpose of the technique that we're going to discuss. It doesn't really matter whether the symmetry is global or it's a gauge symmetry. And the important thing is to understand what kind of singlet operators we can build out of these fields, singlets of the symmetry. Because if we want to have this symmetry, then our Lagrangian must be built out of them, used to build the Lagrangian. So let's introduce some useful terminology. So the singlet operators can be what we call single trace. The origin of this nomenclature is rooted in the example with matrices, which this would really be a trace over some matrix. But it's convenient to just keep using this name also for the vectors. So what are those? These are operators in which we take two of our vector fields and we contract one index, okay? So let me give some examples. So the simplest thing you can imagine is to do some bilinear like that. Or you can form some bilinear with derivatives. Oops. And you can imagine many more examples. So the general rule for a single trace, there could be some string of derivatives acting on one of your vector fields, and then some other string acting on your second field, and they're both at point x. So this can be any combination of derivatives. Okay, I can take derivative with respect to x, or monomials in singlet fields. So if we have some additional fields in our theory that doesn't carry any index, we can also stick it there, and that's still a single trace operator. So if we want to summarize all of this, we can just call single trace operators, all the operators in which there is just one contraction of the index A, okay? So that's the simplest way to say it. Okay? Of course, in the complex case, here I was assuming when I did these real fields. In the complex case, if you want to preserve un, you will have one of the two is going to be a complex conjugate. Okay? So these are what is called a single trace, and then there are other operators which are called double trace. And these are operators of this form, in which we have, so the simplest one would be this kind of quartic operator. So in general, these are operators of the form O1 in X times O2 in X, where O1 and O2 are single traces. So in other words, these are operators in which you have two contractions of the index A, two contractions, and at this point we can let our imagination guess that there is also something called multitrace, and these are just products of k single trace operators, okay? So we have k contractions, and we can call it k tuple trace if you wish. Okay? So we organize in the largent theory operators according to this classification. We count how many contractions we have, and then after we do this, we can. Oh no, I have to use the one above. Okay, I forgot to use this one. And then after we do this, we can start writing down an invariant Lagrangian. And there is this claim that I want to make. So consider the Lagrangian we can write it like this. We put an n outside, and then we have a sum over single trace operators so this is supposed to mean the one that I put here. This one just means single trace. Then we have a sum over double trace operators with a coefficient 1 over n. And we can also have, in principle, any kind of multi-trace couplings. So now I'll put a k here because this is going to be a k-trace coupling. Oops, I forgot the I here. Okay. So, okay means then there is a claim, and the claim is that maybe let me write the claim here. In the limit n going to infinity with g I k fixed, only a subset of diagrams the diagrams survives, let's say dominates. Dominates the perturbative expansion. Okay, so you just write any Lagrangian like that, and in the large n limit with this GI fixed, you will focus on a certain subset of all the Feynman diagrams, and importantly, the important thing is that this subset, they contain arbitrarily high powers of the Gij couplings. Okay, so this means that the family of diagrams we are focusing on by taking this limit, it's a subset that receives contribution at arbitrarily high order in perturbation theory. It doesn't truncate to some order. Okay. So this is the first bullet of the claim that I want to make. The second bullet is that we have methods for resumming them. And this is going to be the topic of the course. We have methods for actually, you see, if I had to compute the full sum over Feynman diagrams, I would be helpless. But in this particular case, since I focused on a certain subclass, it actually turns out that I have some efficient method to perform the sum. Okay, I can do it. And on top of that, besides resumming them and so obtaining full functions of my couplings, I can also set up a systematic 1 over n expansion. Okay. A few comments. So the first comment is that, let me write it here, a parenthetical comment. Like most of the things that we said here apply also for matrix models. Just I mention it, if you might be interested in that. For matrix models, this also applies with some differences. What are the differences? So there are two important differences. One difference is that you have to change n with n squared, okay, in the formulas that we used. So here, for instance, everywhere where you see n, you should put n squared. And of course, the terminology single trace, double trace also refers to, in this case, it's even more intuitive what it means. Single trace means that there is one trace, etc. Another important difference is that this bullet does not apply. So in that case, even though it's true that we just have a subclass of diagram, in that case, in general, we don't have an efficient way to resum all of them. It's still a bit too hard. Okay, so the vectors are, the vector models are much easier in that respect. Okay, so the good news for us is that we now have this, which allows us to compute, but also it contains information about all orders in perturbation theory. Another thing I want to say is that we are not going to give a proof of this claim. This could be maybe something that we can talk about in the discussion if we want to try to make a general proof of this statement. But in this course, we are instead we are just going to see it at work in examples. Okay, so we're going to do examples and we're going to see that this is true. Yeah. What's the question again? Yes. Like once you do the resummation at leading order, this naturally leads to a systematic 1/n expansion. And then when you do this 1/n expansion, you can understand it as resumming all the diagrams that contribute at subleading order and so on and so forth. Yes. Yes.
For matrix model, the planar limit corresponds to the quantum case. In this vector model, what does the planar limit correspond to?
The planar limit just means the leading order, right? It just means you. Yeah, so I will now say what diagrams we resum in the analog of the planar limit. I don't know, maybe we should call it the bubble limit. I don't know, we just basically resum bubble diagrams. Okay? But yeah, I was going to mention it now.
Do you also expect negative critical couplings, the vector model for the G I? Because in matrix models you have negative critical couplings.
Negative?
Yeah, the critical point of your theory in matrix models goes for G negative. Is this still consistent with the vector models?
Well, what we are going to see what happens, for instance, in the ON, and there, yeah, you have a critical value of the coupling, but it's basically the usual phase transition between symmetry break and symmetry preserving phase. Yes. Okay, so just to give a hint of how this resummation works. Am I erasing the right blackboard? I don't know, which one should I erase? I think that one is older, yes. So how does it work? So, idea about the claim. So suppose you take, for instance, this Lagrangian, which is exactly the first one we are going to study in details. The first one we are going to study in details is the one with the quartic interaction. And now I'm using you see, I'm using the general rule. So the general rule tells me to put this n, and then in front of the single trace I have a 1 over n, 1 over root n, sorry. So I end up with this square root. And then I'm going to put some double trace interaction. Okay. Consider this for instance, and let's get some idea of what are the dominant diagrams. It's convenient to go to canonical normalization. I personally like canonical normalization. Don't ask me why I normalize with these two, the quartic coupling, because I'm not sure, but that's what I did, so we're going to stick to it. And so this is just going to canonical normalization. And now you can easily convince yourself, just by doing some counting, that the dominant diagrams are of two types, by which I mean the ones that, so again, we are going to take now n to infinity with lambda fixed, and now I want to give you some examples of infinite families of diagrams that they will survive at leading order, okay? So there are some tadpoles that we have to deal with, and basically suppose you have some line of your fields, and you can look at diagrams in which you attach some closed loop in this fashion. You see, this is my quartic interaction here, and you can convince yourself that these guys are all of order n to the 0. Okay, you can keep adding them where you want. That's not really a mystery, right? It's just because we have an 1 over n in our quartic vertex, right? And then when we close this loop, we get a factor of n. So all of these guys we need to take care of if we want to do the resummation. I'm not completely sure why I call them tadpoles. I meant the ones with this closed loop, okay? It's just because the starting diagram, I mean the diagram that gives rise to all of this is this, which you can think of as a tadpole for the one-point function of phi a, phi a. Okay? So this is one family that we need to take care of. And what is the other family that we need to take care of? Again, I'm very bad at doing things in order. Now this is the one to erase. The other family you need to take care of are the bubbles that I was mentioning before. So imagine this, consider this other family. Okay, so suppose you're doing some 2-to-2 scattering of your vector fields. Then this will be the leading one, but then you're going to have all kind of corrections like this. Okay. And also these ones, you can convince yourself that they all have the same scaling, because you see, when we go from one step to the other, okay, the next, what are we doing? We are adding again 1 power of our vertex and a closed loop. So they compensate each other. So Okay, so these are the two infinite families that clearly exist. And just a comment that you see from this family, this seems a little bit more tame, right? We already see a structure that will make it easy to resum because it's like it's going to be some geometric resummation. This one might look a little bit more worrying, but we're going to see that we're going to be able to sum both. Okay, so before going now to really dirty our hands with the example, I want to mention one more general property of large n, which is important, and that's what's called large n factorization. So maybe first I should have asked if there are questions about this so far. Yeah. Yes? Uh-huh. Mm-hmm. Mm-hmm. Yeah, it's going to be the same. It's just going to be that we are going to exchange this chain of bubbles nested inside some other diagrams. Okay, so at subleading order, this thing will be nested in the, we can give some examples. We are going to compute some 1 over n stuff. Not so much, but something. Okay, now what is the next? Yes, yes. Again? Suppressed? Yes. What is an example of a diagram suppressed? It will be something like, you take this, you do, for instance, your thing, and then now you add, why not? We can add something like this, for instance, okay? And then you see that you did gain an hour power of n, but you added 2 couplings now. So since you added 2 couplings, this is going to be 1 over n suppressed. And you see, once you start with this guy, you also have to consider this guy, and you need to keep going, okay? And reassemble the chain. Other questions? Okay, so the other thing I wanted to mention about general large n, before we move to really do some concrete calculation, is an important property which is called large n factorization. What is this property? It's just the statement that suppose you take an endpoint function of your single trace operators, okay? Then the claim is that if you consider the connected part, then at leading order, the leading order behavior of this, so here I'm putting proportional 2 because I'm just going to write down the scaling with n. So the leading scaling with n is, okay, I will write it like this because then I will explain where it comes from. Times n, okay? And this is, I erased the Lagrangian, but okay, now we'll explain. Okay, so this is the leading behavior, okay? So let me first explain where this comes from, and then we see the consequence. So where this comes from is the leading connected contribution is going to be a diagram like this. You see your single trace guys, they're going to contain, so when you insert your operator, no, the operator is a single trace, so it has 2 lines of the vector fields, so you can draw it like this. Is it clear, this diagram? It just means that you contract This is going to be the leading connected contribution. And then, how do we get this scaling? So to get this scaling, you have to remember our Lagrangian, right? Our Lagrangian was, unfortunately, I erased it, but it was 1 over n, 1 over root n times the single trace, plus So you see, the kinetic term for our vector fields is going to be here. The kinetic term is going to be here. So you see that the kinetic term scales like it has a root n in front, as we saw in our previous example. Okay? So this means that the propagator goes like 1 over root n. Okay? Do you agree with this? Just if you have this 1 over root n here, the propagator is going to go like 1 over root n. And then, you see, here we have small n propagators. So each of them give us 1 over root. And then we have, of course, one big closed loop. And this big closed loop gives us this power of n. Okay? So this is the derivation of this power. Is it clear, the derivation? Are there questions? Okay. And now, I think this is the one I need to erase. What are the consequences of this? The consequences are, well, the important thing is that, you see, this thing is going to 0 when n goes to infinity, at least if small n is 3 or above. So this just tells us that the dominant contribution at large n is the disconnected one. So if you have your correlation function, at leading order is going to be just well, we can drop, of course, the, let me just write it like this. Okay? Let me just write it like this. So the fully disconnected contribution is going to be the dominant one. And so just the product of one-point functions. You see that the one-point functions scale like root n. If on top of that we assume if one-point functions happen to vanish, are 0. This, for instance, happens if you're considering a conformal field theory. If you have a QFT, then the one-point functions are 0, and then the leading contribution, sorry, this I meant plus 1 over n corrections. Okay? Then the leading contribution comes from weak contractions. Okay? What does it mean, weak contractions? I mean that what we're going to have to do, let's give an example of a 4-point function. Okay? Suppose that the 1-point functions are 0, so this kind of leading term that we had before doesn't exist. 1 plus order 1 over n. Let me write it like this. So suppose that there was not a plus, it was 1. Okay. Suppose that those 1-point functions don't exist, so then we are going to have to factorize this in 2-point functions. Okay? And the way this factorizes in two-point function is that we have to do basically contractions between our operators. So for instance, we can decide that we have the two-point function between these two and these two, or the two-point function between this and this, and so on, okay? So this is gonna be now the leading order term is gonna be a product of two-point functions plus permutations, everything 1 plus order 1 over n. Okay? And so you see the magic thing is that this kind of, in this kind of limit, our single trace operators start behaving a little bit like they are free fields, you see? We can compute their correlation functions. Okay, after we subtract their tadpoles, in quote, we can compute their correlation functions just by doing weak contractions. And this becomes a very concrete statement for those of you who have studied it, like in the context of holography. You're going to discuss a little bit in the course by Roberto, I believe. And so in holography, indeed, one finds some fields that are free at large n and correspond to our single trace operators. Questions? Uh-huh.
So the one-point functions are the leading order, but if they're zeros, now these two-point functions should be order 1 over.
So these guys are the leading ones you see from here, right? Is root of n, and then the 1.5, the two-point function instead go like n to the 0, okay? So here I'm assuming that the one-point functions are 0. So what is the question? Sorry.
So the two-point functions are now 1 over n, or
So this guy was actually not order n to the 0. I mean, this a little bit all depends on the precise normalization you choose for the single trace operators, but certainly the leading order was the product of n-point function or one-point functions, which in this normalization was something like root of n to the power small n. Okay, and then I wrote here multiplied by 1 plus 1 over n corrections. Okay. Once those are gone, the one-point functions, you get this, which in our normalization we are using now, it's order n to the 0. Okay? And also this statement about large n factorization applies the same for matrices. Just with n that goes to n squared. Okay? I think this is the right moment to do our 5 minutes break, and then we continue. Okay, it was a bit silly to think that we can do a 5 minutes break, but I will not make this mistake again. So let's continue. So now we really are going to start dirtying our hands. With the first example. So let's consider this model in RD. And D can be 2 or 3. So this is the model defined, the one model is defined by this Lagrangian. I'm using the version of our Lagrangian seen before with canonical normalization. If you remember, with the canonical normalization, in front of the double trace operator, I had the 1 over n. And this is now a theory for ON vector of real scalars. Real scalars, and there is an ON global symmetry where the name of the model comes from. okay? So first comment I wanted to make is that it is consistent in the technical sense of the RG to stop here and include only up to the quartic interaction, okay? And as a topic, for instance, we can discuss it a bit today. I will not give you now the proof, but you can try to think about it. So it's consistent to stop and not include higher orders. So what do you have to, like phi A cubed. So what do I mean by consistent? I mean that if we start with a Lagrangian like this, these higher order couplings, like the sextic one, are not going to get generated. Okay, so try to convince yourself that this is the case, and we can discuss it a bit this afternoon. So that's our Lagrangian. You see, it's a Euclidean one, so that's my convention. So I like Euclidean, and again. No, you can include it. I'm just saying that it is consistent not to include it. This means that if I don't put it, it's not going to be generated. So the logic I'm using is sometimes, I can start with some Lagrangian and I decide to randomly put some things to 0, but that's not consistent with the RG because I do one step of my RG and all these other things are going to get generated, okay? So what I'm saying here is that this is really, the RG is just going to remain within this set of couplings, okay? So you can try to convince yourself that this is the case. And otherwise we're going to see the reason today in the afternoon. This is also for finite n, this observation. Okay, and note that in D equals 3, this contains actually all the relevant couplings that we can build out of the scalar field. While in dimension 2, this is not true because in dimension 2, all the possible higher order terms are also going to be relevant. Okay, this is just a parenthetical comment. Which one is the next? I think this is the next. So for the reason that we already saw in the introduction, this theory is a strongly coupled theory in the IR because if you go and compute what is the mass dimension of this coupling, you're going to find that this is 4 minus d, which for us is going to be then bigger than 0. And so we have strong coupling. The IR at large distances. And nevertheless, we can, it's worth trying to first guess some of the properties of this theory just by looking at the potential, okay? So let's see how far classical physics can guide us. So what would we predict just by looking at the classical potential? Well, our prediction would be the following, would be that we have a phase for positive mass squared, where our potential looks like this, right? Our potential looks like this, and we just have one stable minimum where our phi field doesn't get above. This is the quartic coupling, we are going to take it positive for stability. And then we would say that instead for negative mass squared, the potential suggests that we are going to have a symmetry breaking phase, okay, with the Mexican hat shape of the potential. So this is 0. And so what would we predict? We would predict that here there is some gapped phase of our. So gapped phase is just a fancy way to say that all the excitations are massive, okay? because the second derivative of our potential at the minimum is positive, is strictly positive. We would say that this is ON preserving. And there are some massive objects, some massive particles that we can scatter that are n massive particles in the n of ON. Okay, so that's what we would say about this phase. And then classical physics also suggests that on this other phase we're going to have some gapless phase. Again, just a way to say that there are massless particles, because you see we have the spontaneous breaking, so some of the second derivative of the potential has some zero eigenvalue, and so we would say that there is spontaneous symmetry breaking from ON to n minus 1 with Goldstone bosons. So we would predict that here we have n minus 1 massless Goldstones plus 1 massive radial mode. And again, just the analysis of the potential tells us that here in between we should have some transition, right? Some second order phase transition. Second order just means that it's a continuous one. You see all the vacua move, all the vacua that we have here continuously merge and coincide with the vacuum that we have on the other side. So we expect here to have a second order phase transition. And so this should be described by some massless and interacting degrees of freedom. Okay, so that's what we would expect. And let's anticipate what we're going to find by doing a more quantitative analysis. So this qualitative picture remains basically true in d equals 3. Everything that we said here, it's true. And so large n, going to the quantum theory and using large n, we are going to be able to do just two things. We are going to be able to first compute, like assign some quantitative bonds to some quantitative flash to these qualitative pictures. And another thing that is going to change is that in d equals 3 is that it's not going to be true that we really have a massive particle corresponding to the radial mode. We are going to see why. The situation is much more drastic in 2 dimensions, because basically in 2 dimensions what's going to happen is that all of this part does not exist. Okay, so in 2D all of this is going to be modified. Okay, we are just going to have this part that remains true. Okay, so that was like just some spoiler. So our objective now, our goal is to use large n to see what remains true of this qualitative picture. And actually compute observables. So what are the observables that we are going to, so what can we expect to be what is there to compute in this model? So we need to distinguish two cases. So if we are away from the phase transition, the most basic observable that we are going to consider is basically scattering data. Scattering data, which includes also inside the information about particle masses and their decay rates and so on. Okay? So that's what we want to compute either on the spontaneously broken phase or in the symmetry preserving phase. While when we are at the phase transition, what is going to be our goal there? There we want to compute something that is called QFT data, okay? And these are basically scaling dimensions. And OP coefficients. Okay. So what I'm using here is that the description of this second order phase transition in terms of quantum field theory is given by QFT, okay? And then, so when we sit here, we are going to compute observables of this QFT, which can be encoded in this so-called QFT data. Now, I don't want to completely assume that all of you already know something of QFT, so just let me give a brief description of what the QFT data are. Okay, so in the phase transition, the theory does not contain scales. It's described by a QFT. So QFT stands for conformal field theory, and it's a theory in which the symmetry is enhanced from the SOD rotational symmetry is enhanced to the group SO1 D plus 1, which is the Euclidean conformal group. And so this guy basically extends the rotation. If you prefer to think Lorentzian extends, I should have said extends the isometries. So if you are in Euclidean, we have translations and rotations. And if you prefer to think Lorentzian, you can think of Poincaré. So extend the isometries by the dilatations. Okay, with some generator that we call D. This just means that we can, since we don't have any scale, we can freely perform dilatations of our space-time vectors. But in addition, there is also a surprise that we get an additional generator, and these are called special conformal transformations. Okay, there are 4 of those. We call them K mu, so they're a bit like, we have, sorry, 4, not 4, I meant there are D of those, okay? This ranges from 1 to D. So the generator is a vector, is a rotation vector. And when we are in these theories with this symmetry, what do? Is that the first thing is that we concentrate, so the interesting observable when we have this symmetry, interesting or if you wish, the most basic observable, is the correlation function of conformal primary operators okay. So here I'm just to make sure we are on the same page, I'm just opening now a small parenthesis to explain what are the things that we are going to compute at the phase transition. So it's a small parenthesis about CFT. So what are these conformal primary operators? Using this generator K, it is a generator K mu, we can define something called a conformal primary by this condition. Okay, so these are what is called a primary operator. And so it so turns out that once you know correlation functions of these primaries, all the other correlation functions in the theory are just basically derivatives of them. Okay, so in terms of them, you can use the conformal symmetry to reduce to just to the correlation function of these simpler guys. And the first piece of what I call CFT data comes from looking at how these primary operators behave under scaling. Okay. So if we perform a dilatation and we commute it with these primary operators, we get a number which is called the scaling dimension. And the finite form of this commutation relation is just the statement that if we have the primary operator in the point x and we do a rescaling, we get the scaling factor. Maybe I shouldn't call lambda like the coupling, let me call it alpha. Okay, if you do a rescaling of your point by a parameter alpha, you just get this power in front, okay? Controlled by the scaling dimension. And then, for instance, if you compute, so delta controls the 2-point functions. If you compute 2-point functions of primary operators, you're going to get something like this. So they're only going to be non-zero if they have the same scaling dimensions. And then it's a power law of the distance. Okay, it's a power law of the distance. And in principle, if you have many operators with the same scaling dimensions, you might also get some matrix here, okay, that mixes among them. So if you have many operators with the same scaling dimension delta, you also have this one, but this matrix, you can always orthonormalize it. You can always, just by doing some redefinition of the fields, you can always orthonormalize it. And take it to be just delta ij, okay? So the first piece of CFT data are these conformal dimensions, which are just what controls 2-point functions of primary operators. Here I simplified a bit my formula by assuming that my primary operators didn't have spin. If you have spin, you just have to add some indices, okay? It's not a big deal, you just have to add some indices. And once you know how to compute the 2-point functions, higher point functions are computed, at least in principle. You can always reduce them two two-point functions using something called conformal OP. OPE stands for operator product expansion, and this is some formula of this sort. OI in some point y. So in CFT we can rigorously prove that if we take two operators and we push them on top of each other, if we push them on top of each other, we can replace this by some convergent sum over other primary operators, okay, and here you get some coefficient, then you get something which depends on the points and soaks up the scaling. Let me write it bigger. So this is x minus y to the power minus delta I minus delta j plus delta k. Okay, I hope it's readable. And then you have here times the operator k at point x plus, these are infinitely many terms, which I'm not going to write down. And these are terms with derivatives of OK with coefficients fixed by symmetry. Okay? So all the complicated part of this expansion is here, but it is complicated, but it's also fixed by symmetry. Okay? So the only part of this nice formula that is not fixed by symmetry are these coefficients over here. Okay? So these are really dynamical part of the thing, and these are called OP coefficients. These are dynamical, not fixed by symmetry. Okay? And you see, so now if you have some higher point correlation function, what you can do is that using this, you can reduce the number of operators appearing. You see, we have two operators on this side and only one operator on the other side. And so you can do this iteratively until you get just two-point functions. Okay, if you're a purist, you could also have done it here and say that you get the identity. But okay, so this was a bit of a fast review of the essentials of conformal field theory, and it was to motivate the fact that interesting observables are the scaling dimensions and the OP coefficients. Okay, so now we can give some names here. Okay. One important thing to maybe I just want to mention from this strategy, one important example is the conformal three-point function. Let's just write it down. Okay. So if you use this strategy for the three-point function, you get this famous formula. Okay, so one way to also characterize these coefficients is as the coefficients that appear in the 3-point functions. Okay. So now we set our goal. Our goal is to take the theory and to see if we are able to say something at strong coupling. We are going to be able to, we should be able to compute these observables in the outside of the phase transition and these observables at the phase transition. Okay. I think maybe now we can stop and then we continue after lunch.